So in this video we want to look at the idea of similar figures. We'll do a couple of videos on similarity. It's quite an important feature of the geometry and measurement module. So I want to look generally in this video at the idea of similar figures. Okay, a figure being a two-dimensional shape. So two figures are similar if one is an enlargement of the other. So similar figures have the same shape, and that is the same internal angles, but they're of a different size. So in similar figures, all side lengths have been increased or decreased in the same proportion. So say, for example, you might have doubled all of the side lengths, thereby creating an enlargement with a scale factor of 2, but the shape maintains, the figure maintains the same shape. If you've enlarged all of the side lengths by the same proportion, you're going to find all the angles are still in the same places, and therefore the two figures still have the same shape. So here we have two quadrilaterals, quadrilateral being a four-sided shape, A, B, C, D, and P, Q, R, S, and they are similar because these two things are true. The magnitude's another word for size. We tend to use magnitude when we're talking about the numerical size of something. The magnitude of the corresponding angles is equal. Okay, so each of the corresponding angles, so we can see here if we orient the shapes in the same direction so that they look exactly the same, just one being an enlargement of the other, we can see that vertex A corresponds with vertex P, and so therefore the angle at A should be the same as the angle at P. And actually that one's 90 degrees, so that one should be labelled that way. We can see therefore that the angle at B is also the same as the angle at Q, the angle at C is the same as the angle at R, and the angle at D is the same as the angle at S. So if all the side lengths are, all the angles are equal, you know you have similar shapes. You want to make sure that you reorient them so they're both drawn the same way up, so you can really clearly see which sides correspond with the others. So they're similar because all of the angles are equal. And they are also similar because the ratios of the corresponding sides are equal. Okay, so I can see that PQ, this side length, corresponds with this side length. So when I do the side length of PQ, which is 20, divided by the side length of 8, I get a ratio of 2.5. So that's telling me that this bigger shape is 2.5 times bigger than the smaller shape. We're essentially calculating the scale factor by dividing one of the side lengths by its corresponding side length. But the important thing is that it needs to be the same for all four sets of sides. So again, we want to look at, all right, well, if I did QR divided by BC, so 15 divided by 6, that's also 2.5. Okay, so all of the side lengths, you can check them individually. All of the side lengths have been multiplied by 2.5 from the smaller triangle to the larger triangle. Equivalently, if we'd done the division the other way, so if I'd done 8 divided by 20, okay, 8 divided by 20, Control Enter to get that as a decimal, that's 0.4. And it's similarly 6 divided by 15, 6 divided by 15, that's, oh, sorry, typed the wrong thing in, let's go again. 6 divided by 15 is also 0.4. Struggling today. 6 by 15 is also 0.4. We should again be able to check 17.5 if I divide that by its corresponding side length, which is 7. That's, did it the wrong way around. Let's try again. All right. 7, sorry, the smaller one, 7 divided by 17.5. That's also 0.4, and 8 divided by 20, that is also 0.4. So to go from the smaller shape to the larger shape, we clearly have multiplied by the side lengths by 2.5, but to go from the larger shape to the smaller one, we've multiplied by 0.4. Okay, so there's always going to be two scale factors. There'll be the scale factor to enlarge and the scale factor to reduce, but they're essentially the same thing. Multiplying by 0.4 is actually the same as dividing by 2.5, which is the opposite of multiplying by 2.5. So if you look at 1 divided by 2.5, it is 0.4. Okay, so multiplying something by, the opposite of multiplying by 2.5 is to divide by 2.5, but dividing by 2.5 is the same as multiplying by 0.4. So in terms of scale factor, there's usually two two scale factors, but more often than not, we'll talk about the enlarging scale factor, so the one to get from the smaller shape to the bigger shape. And so to work that out, we're going to take the larger side length and divide it by the smaller side length. So 20 divided by 8, so we get our 2.5, and it's the same for all the pairs of side lengths. Okay, so here we can say, so some notation, that ABCD is similar to, okay, we use this squiggly line symbol, which is called a tilde. So ABCD is similar to PQRS. Now, when we make that statement that ABCD is similar to PQRS, the order that we list the vertices in is important. So this statement, without seeing any diagrams, tells me that the vertex A corresponds to vertex P. That is, the angle at A would be the same as the angle at P. Vertex B corresponds with Q, C corresponds with R, and D corresponds with S. So it would not be correct to say that ABCD is similar to RSQP, okay, for example. So that's not correct. So it's really important that the order that you list the vertices in matters. Okay, we've talked a bit about this next bit. We can also observe that the enlargement factor or scale factor between the two shapes is 2.5. We often use the letter K when talking about the enlargement or scale factor. K equals 2.5. And that is that all the side lengths in ABCD have been multiplied by 2.5 to produce PQRS. As I said, if we were to do the divisions the other way around, dividing the smaller side length by the larger side length, we would get the scale factor that allows us to reduce the shape, to go from the bigger shape to the smaller shape, and that was 0.4. So the enlargement or scale factor from PQRS to ABCD is 0.4. Note that we would still call it an enlargement factor, so that's why we tend to use a scale factor. It's a bit less misleading. So yeah, but as I said, multiplying by 0.4 is the same as dividing by 2.5. So it is still the same scale factor of 2.5. When solving problems involving similarity, we can either make use of the scale factor, so we can calculate the scale factor and then use that, or we can set up a ratio statement, and I'll show you how we can use those things. So by ratio statement, I kind of mean this kind of idea. So in this particular shape, we know that if we took the side length PQ and divided it by the side length AB, that's the same as if we had taken side length QR and divided it by side length BC. So let's say this is an unknown thing, but you know all of these, you essentially get, so let's say, what's PQ? So 20 divided by 8 equals, let's say we didn't know QR, x divided by 6, we could solve that equation to find x, okay, rather than ever have to work out the scale factor. If the scale factor is a nice number, if the scale factor is everything's been doubled or tripled or whatever, then absolutely I would work with the scale factor. But the scale factor could be something quite unpleasant, in which case there's actually no need to work out the scale factor. You just use the idea of the ratios of the side lengths being the same. Okay, so let's look at some different examples. So the figures pictured opposite are similar. So this question is telling us that they're similar, so therefore we can use the properties of similarity. We want to calculate the scale factor. So we need to see where there is a pair of side lengths where we know about the length in both of the shapes. So for example, this 50 and y, well, we don't know what y is, so we can't calculate the scale factor from that. 70 corresponds with x, but we don't know what x is, so we can't calculate the scale factor from that. So the pair of information that's useful for the scale factor is the 50 and the 200. Okay, so in terms of part 1, our scale factor k is going to be 200 divided by 50. And so the scale factor is 4. The pink figure is 4 times larger than the blue figure. It would also be correct to say that the scale factor is 0.25, 1/4, because multiplying by 4 is the same as, if we're going back the other way, we divide by 4, which is multiplying by 1/4, or multiplying by 0.25. Okay? So either of those scale factors would be correct answers to the question. Okay, part 2. Find the values of x and y. Okay, so we know that to get from this shape to this shape, we multiply by 4, and so therefore we can see that x is going to be 70 multiplied by 4, which is 280, and there's units, isn't there? Centimetres, yep. And we can also see that y, we're also going in the same direction, is going to be that 50 centimetre from the original shape multiplied by 4, so that is going to be 200 centimetres. You could also see that these are the same length here, so these are going to be the same length here. Okay, part B. The figures pictured opposite are similar. calculate the value of x. Okay, I would strongly encourage you to start, before you deal with problems with similarity, to reorient your shapes so they're both in the same direction. Okay, so this one's upside down compared to this one, so I'm just going to redraw this one so that it's in the same orientation as the larger one. Okay, sorry. Okay, so we've got isosceles triangles, that's 3, so it's Z up the top, okay, and we've got X and Y down the bottom. It doesn't really matter which way X and Y go because it's an isosceles shape, and so this length is 2. Alright, so in terms of thinking about the scale factor we're going to be able to work out from there. Okay, so 5 divided by 3. So because that's not a nice number, 5 divided by 3 is a recurring decimal, 1.6 recurring. Personally, I wouldn't bother to work out the scale factor here. If I want to find the value of x, I would just use the idea of the ratios within the similar triangles. Okay, so I know that x divided by 2, so x divided by its corresponding side length will be the same as 5 divided by 3. So this is where I would just go straight to the ratio rather than bothering to work out the scale factor. If the scale factor is a decimal, especially an ugly recurring decimal, I wouldn't work with the scale factor. I would just work with the ratio. So we know x divided by 2 is the same as 5 divided by 3, and so therefore to solve for x we just need to multiply both sides by 2. Multiply both sides by 2, so it's 5/3 times 2, which is actually 10/3. Okay. Now it doesn't tell us to give a rounded answer, so if you love decimals, if you love decimals and want to write it as a decimal, you can, but it's not 3.3, nor is it 3.33. It's 3.3 recurring. Okay. If the question doesn't tell you to round it off, then you should leave it exactly. So you can leave your answer as 10/3. That's a simplified fraction, or you can leave it as 3.3 recurring. So as I said, if you've worked out the scale factor is 5 divided by 3, which is 1.6 recurring, and so therefore x times 1.6 recurring would give me 2, and so therefore x is 2 divided by 1.6 recurring, which should give me 3.3 recurring. But it's just a bit messier with all those decimals and still trying to work exactly. Personally, I find it easier to start from here and then solve. If you're not comfortable with the solving process, again, you've always got a CAS in Further Maths. Get your CAS to solve it for you. Solve x divided by 2 equals 5 divided by 3 for x, enter, 10/3. Control enter, 3.3 recurring. Okay, so just set it up using the ratios. This side length divided by its corresponding side length equals another side length divided by its corresponding side length, and then you've got an equation that can be solved. Okay, part C, the figures pictured opposite are similar. Calculate the value of y. Okay, so again, the first thing I want to do is reorient them to make sure they're in the same order. So the biggest thing for me that's helping me orient it is to line up the alpha with the alpha. Okay, so if I think about, it doesn't need to be perfect. Oops. Okay, so let's say that's got to be alpha down there, so that has to be D. That tells me that has to be D. All right, then if I look at the side lengths, in terms of the two side lengths next to alpha, the bigger one is on the bottom. Okay, this is the larger one. 15.6 is bigger than 12. So in the smaller triangle, I've got 13 and 10. So it must be the 13, the larger one that goes down the bottom, and the 10 that goes here. And therefore that leaves 12 to go over here. All right. Okay, so now I can basically ignore that one. I'm looking at these two. I've got them in the same orientation. So I can now look at what I'm working at. So I want to find the value of y. So y is a length here. In terms of working out the scale factor, I've actually got 2 bits of information that would allow me to work out the scale factor. 12 and 10 correspond, and 15.6 and 13 correspond. So our scale factor is 12 on 10, which should be the same as 15.6 on 13. So let's just check that. 12 divided by 10 is 1.2. 15.6 divided by 13 is, CAS is ignoring every third tap I do, is also 1.2. So the scale factor is 1.2. So you could use the scale factor of 1.2. So I'm just going to do it in 2 different ways. So we calculate the scale factor, and then we can use the scale factor to say that, okay, well, y times 1.2 must give me 12. Okay, so that's this one. Y times 1.2 must be 12. and so therefore y must be 12 divided by 1.2, which is 10. Okay, so actually it's an isosceles triangle, but we didn't know that. There was no information that told us that before we did the calculation. Okay, so that would be using the scale factor, or you could just, and I tend to opt for the second option. I always use a ratio sort of method because I don't bother to ever work out the scale factor. So all I would be doing is saying, okay, well, sorry, my pen has stopped working. All right, all I would be doing would be saying y divided by 12, one side length divided by its corresponding side length is the same as 12 divided by 10. Or you could use 15.6 divided by 13, doesn't matter, it'll give you the same result. And so then I could get my CAS to solve this equation if I want. Y divided by 12 equals 12 divided by 10, solve for y, and it tells me that y is 7215, which if I want that as a decimal, control enter is 14.4. Or if my equation solving is okay, I can do a bit myself. 12 divided by 10 times 12, which is 144 on 10, and so therefore that is, oops, why have I ended up with two different answers depending on my two different methods? Something's not right here. Let me just have a quick look. Apologies, I've worked out my error. I've realised that this is not right here. I've got the timesing by the scale factor around the wrong way. So actually, and it's because the diagram's a bit misleading, it looks like the smaller triangle, the triangle that looks smaller is actually larger. So I'm just having an issue with my pen for a minute. Just let me pause and reboot. Okay, so the issue is actually, it is this way. We're timesing by 1.2. So my scale factor is 1.2, and so therefore I actually know, I've got this calculation around the wrong way up here, that y is going to be equal to 12 times 1.2, and so that is 14.4. We do it that way. So 12 times 1.2 is 14.4. Okay, alternatively, as I said, you just start off by setting up a ratio statement. Y divided by 12 is the same as 12 divided by 10. Get your CAS to solve that for you. It will get you straight here, or solve it by hand, depending on how strong your algebra skills are. Okay, the scale factor could also be given as a ratio. So maps, we often see scale factors given as a ratio. So a map is drawn using a scale factor of 1 to 2000. So that means that one unit of measurement on the map is equivalent to 2000 times that unit of measurement in real life. Okay. So the distance from a campsite to a river is measured to be 8 centimeters on this map. Find the actual distance. Okay. So from the map to the real world, we're multiplying by 2000. Okay, so therefore to go back the other way, we would need to divide by 2000. Okay, so we're going from the map to the real world. Okay, so the actual distance is going to be the map distance, which is 8 multiplied by 2000. Okay, and so that is going to be 16,000 centimeters, which is not that useful a unit in the real world. So maybe let's divide that by 100 to change it to meters, so that is 160 meters. Although the question didn't specify the units, so this would have been a correct answer to the question as well. So either of those. Or I guess, you know, what's that going to be? 0.016? A 1,000 times 0.16. So, sorry, just 0.16 kilometers. Any of those would be the same thing. Part B, a section of the walking track is 500 meters. How long would this walking track be on the map? Okay, so first thing I'm thinking, one of the things I want you to get used to when you're working with geometry and measurement problems is, does my answer make sense? In fact, any sort of problems, that should be the case. But I'm thinking, right, 160 meters in real life was 8 centimeters on the map. So 500 meters is going to be, you know, about 3 and a bit times 8 centimeters. Okay, so you should have a sense of scale as to what your answer should be. Okay. So we know that the actual distance, so we know that the map distance, we're going to need to divide by 2000 to go from actual to the map. So the map distance is going to be the actual distance, which was 500, divided by 2000. Okay, so 500 divided by 2000 is going to be 0.25 but don't forget, we need to be consistent with that with units. So the 500 was in meters, so that's 0.25 meters, okay? And so therefore, 0.25 meters is 25 centimeters on the map. So as I said, a bit more than 3 times the 8 centimeters we saw in the previous question. Again, 0.25 meters is a correct answer to the question, unless it specified what units you should use. Okay, so similar figures, there's a worksheet for you to do as practice today.